Fine. Okay, hope it is visible also. Okay. Okay, fine. So last class, we were actually discussing about a typical example of maybe a pattern recognition problem. So we started with an artificial data, which was actually maybe created from a sine 2 pi x function, and then we have added maybe random noise. Okay, so that means we have got this particular set of maybe say blue points, and then we have defined a general polynomial, okay, of order m, okay, and so our aim is actually to fit a polynomial of m degree, so that that polynomial will fit the blue points in the best way, or maybe as close as to the original function that was a sine 2 pi x function. So that is actually our aim, okay. And then we have seen maybe different cases for em, so that means we have m is equal to 0, okay. And before that we have defined maybe how we can evaluate maybe the error that is involved in the maybe model, okay, that we build, and with respect to the original function, okay. So that is we define an x vector, okay, and a target vector t, okay, and then this is a we assume that this is a function, okay, this is a predicted values, okay, along this particular curve, and then we can evaluate the difference between the predicted value and the target value is actually the value that is given, okay, maybe in the form of a labeled data, because this problem is going to be a regression problem, okay. So because we are actually predicting or curve fitting, okay, we are trying to fit it. So anyway, we are actually trying to find the difference between the predicted value and the target value, and we are taking the square, that is error function that we define, that also we have seen, okay. And so there are n points, so that is why we are summing it over, okay, the n points, okay. And then we have seen what is the case of m is equal to 0, because when m is equal to 0 we don't have any polynomial, we have a constant value. So that means this red one is the curve that we fit, okay. And we can see that what we are trying to achieve is actually the green curve, okay. But it is very far from the original function, okay, that generated the blue points, okay. But we know that there is a component of maybe noise also, so that is why the blue points are actually shifted away from the original maybe the sine 2 pi x function, okay. So that is m is equal to 0 case, and m is equal to 1, okay, we have maybe a straight line of this maybe shape. So that is compared to this constant case, we are having a better fit, okay. So we can try with m is equal to 2, m is equal to 3, okay, whatever, okay, number. And we have seen m is equal to 3 is very close to the original one, okay. So m is equal to 3 means we have to come to this particular equation, okay, where we have a w0, so we have a x, okay, x square and x raised to 3. So up to that point we'll have okay, that particular say function, okay. And so that is a m is equal to 3 case, okay. So that means the red one is actually the curve that we predicted, okay. So it's very closer, okay. And then we have seen maybe a very large value of m. So what, because what will happen, okay, if we increase m, okay, too large, so that means that is a case when we have seen a specific case of m is equal to 9, where we have seen that okay, the curve that we try to fit is actually exactly going through the blue points, okay. So that means it is a perfect fit. But our aim is actually to maybe obtain the original curve, so that is the original function that actually generated the blue points, so that is actually the green curve. So we can see that even though this particular set of points are actually well connected through the our predicted function, that is not near to, okay, but It is not an approximation to the original, maybe the green curve. So what can be the problem is, whenever we have a new x value comes, because this is an x value we have taken maybe from 0 to 1 at this intervals. So that means first one, this one, okay, second one. So that means there can be other values in between also. Okay, or there's a chance that we'll have more values along the say wherever. Okay, because it's a normalized one, but we can assume that there are an infinite number of values maybe that we can go for x. Okay, so in such cases we can see that there's a problem, okay, in this particular case. So that is actually called, the issue is called overfitting problem. Okay, so that means our predicted function is actually fitted exactly through the points. Okay, so that means that particular issue is actually called the overfitting problem. Okay, so the problem with the overfitting is, whenever a new case come, okay, so that means for future x values, okay, so the prediction will be mostly it is going to be wrong. Okay, but in training phase, okay, because whenever we try to build, okay, this particular red function or the red curve, that process is actually the training phase. But whenever we have a new value of x which is not already present in this particular, say, sampling, okay, or particularly not present in this particular say blue points that we have considered so far, then there's a chance that the value predicted, that is a t target value predicted, is going to be wrong. Okay, so that we can easily obtain through maybe this particular plot. So that means we define a new term, that is RMS value of maybe error, because error function already we have defined. Okay, and then we have that's a root mean square value. Okay, so we define using this particular equation, where ew star ew we have already defined, and w star is nothing but the optimal value of w. Optimal value means maybe the best value of w that we think that that is the best maybe representing the that blue, sorry, that our model, that is a predicted curve. Okay, so we can see that whenever we increase the value, or for various values of m, we can see that initially we can say that the error actually decreases, that is a training error as well as a test error actually decreases. Okay, but after maybe a particular value of m, that means we are having, there's a chance of overfitting happens, maybe say for example in this case m is after m is equal to 8. So or you can say from m is equal to 9, there is a chance of overfitting. So that's why we have whenever overfitting occurs, we can say that the training error is almost zero. So that means when we look into the training, we can say that that's a very well trained, or that's a best model that we can build. But that can result in a very high value of say test error. So that is going to be a very bad choice. Okay, because our model is not generalizing well. Okay, for the unknown cases or maybe future values, there is a chance that the model will predict it wrongly, most probably. Okay, so that is a problem with the overfitting, and that is going to be a very important issue that must be taken into consideration while designing any maybe pattern recognition problem. Okay, we will see some techniques. Okay, but before going into the technique, maybe in detail we'll discuss later, but we'll see what will happen to the w, that is the parameter, that is the coefficients of the x, okay, in the polynomial that we fit. Okay, and this is actually an analysis that is obtained. So here we can say that we know that there are, say, different values of coefficients, w0, w1, w2, and w3, etc. Okay, and star represents they are going to be the best values that we find out in some way that we will study later. Okay, for different cases. So here we assume that we start with an m is equal to 0, m is equal to 1, m is equal to 3. Okay, maybe m is equal to 9. The four cases that we have just seen. Okay, so these are maybe a set of values, the w values obtained. Maybe this we can also calculate it. Okay, from the previous equations, from the previous data points. But a very interesting thing is, when you look into m is equal to 9, that is, we know that m is equal to 9 is actually a bad choice, because that result in a overfitting problem, okay, overfitting scenario, okay. And so what will happen is, how that overfitting curve is obtained is, you can see that the w values are going to be very large, okay. So whether it is negative or positive, they are going to be large in magnitude. So that value, that specific value, is actually found out by the training process, okay, exactly to fit the curve through the training data points, okay. So that means we will not have a good generalization, okay, because whenever the next x comes, okay, it will not be able to correctly find out maybe the best w value, okay, that can predict in the best way, okay. So that's the issue. But if you look into, say, m is equal to 3, you can see that it is reasonably, the sizes are actually very small in size, and also maybe very closer also, okay. So but m is equal to 1, we can say that it's a wrong choice, okay. So this is a way, the problem with the maybe overfitting, okay, where the weight values or the coefficients, whatever the parameter values, okay, are going to be finely tuned to that specific set of data points. So that is one issue, okay. That means we taken into consideration. Suppose, okay, so here we can say that we have only 1 2 3 4 5 6 7 8 9 10 points only we have taken, okay, or maybe we have sampled from the say the possible values, okay. Suppose we increase, okay, there's a, so because in this case, these 10 points are the size of the data set that we are having, okay. So we have only 10 points for training, okay, or maybe for building the data set. Suppose we have a scenario where we have more data. So that means instead of 10, suppose we are having 15 data from the distribution that we consider, okay. And suppose we consider the m is equal to 9 itself, okay. So that means we are trying to see what will happen to the overfitting case when the size of the data set is actually increased. That's what we are trying to look into, okay. So here we can see that when you are having more data, okay, maybe 15 from 10, so with the m is equal to 9 itself, you can see that that the overfitting problem is reduced. So that means the red curve is, okay, more or less very close to the original curve, even though not the best, but we can say that means, suppose if we increase to n is equal to 30 or n is equal to 50, okay, then there's a chance that with m is equal to 9 itself, we can obtain a very good maybe say prediction. So that is a case, okay. So that is a significance of data size also. So in any pattern recognition system, if you are having more data, then your model that will be building is going to be better, okay. That is a generally accepted maybe say maybe rule, okay. So that is a one interesting point that we have to note. But there are situations where we will not have we don't have that luxury of having maybe say large data size. Because especially in medical field, we will not be able to get too much say data, okay. So that means there is an issue. So that means anyway we should have to be prepared with for maybe overfitting and maybe techniques to avoid, okay, overfitting, okay. So that is one thing that we have to always think of, okay. Suppose we have a n is equal to 100 case, okay. Again, still we are having the same, okay, polynomial with of order 9. Then you can see that it is very good fit, okay, almost fit to the our original say green curve, okay. So that is a way maybe the more number of data maybe help us, okay, in avoiding overfitting. So there are actually no such rules to decide maybe say here, okay. Before going to that point, so here this m, okay, that is the order of the polynomial that we trying to maybe find out. So that actually determines the model, okay. So here the model that we are trying to build is actually the polynomial. Okay, so that means the choice of m is very crucial here. Okay, and that actually maybe depends on the available data size also. Okay, so that you have to keep in mind. Then now we will see there is a technique. Okay, there is a technique. Okay, because we don't have that luxury of data always, so there should be some mechanism to have a balance between, okay, say this balance in this particular case. So hence we have a technical regularization. Okay, so that is nothing but along with the error function that we have already defined. So this is a error function that we have already defined. We add something like a penalty also. Okay, we add a regularization term also. Okay, that will penalize maybe large maybe weight values or parameter values. Okay, so that is so that will result in maybe large error, so that whenever we are having large error we will not choose that w. Okay, because ultimately our aim is actually it's a minimizing the total error, it's a minimization problem. So because it's an optimization problem where we try to minimize the total error, and we are trying to find out the w vector. Okay, which will result in the minimum error. So that is actually the minimization problem that we are trying to solve. So that means suppose if you are adding another term, so which is lambda by 2 into modulus of w square. Okay, we will see what is lambda, and okay, w is we have already defined. So it is w square is going to be the sum of the squares of the parameter values. That is a w0 square, w1 square, w2 square, etc. Okay, so that's summation. And lambda is actually maybe a user controlled parameter. Okay, so that will that will decide maybe how the final error function must be. Okay, so here e tilde w is actually our final error function. Okay, in the, if you are considering the regularization also in the model. Okay, so we will see different cases because when lambda is equal to 0. Okay, when lambda is equal to 0, we can see that this regularization term will vanish. Okay, so that means our error function will be the same as the previous error function that we have, that is sum of square error function that we have already seen. Okay, then when we increase lambda, okay, so that term will be added to the total error. So and for large w values, so that means whenever we have maybe uh, maybe a set of w with this one. Okay, so that means we can see that these are very large values. Okay, and when you take the square of this one, this is going to be very large number. Okay, so in such cases that will have an impact on maybe increasing the total error, so that this set of w will not be taken by or that will not be, or that model will not be selected by our algorithm. Okay, so that is the idea of adding a regularization term also to the total error. Okay, so that is a point. So lambda is equal to 0 is one case. Lambda is large value. So we will see some set of plots where the log of, okay, this lambda is taken. Okay, and uh, maybe the regularization term is actually added. Suppose we have a value, okay, where ln of lambda is equal to minus 18. So these are some typical examples they have taken, or that can be that are having some specific but importance. Okay, or maybe specific interest maybe in our problem that we are discussing. We can try with the different lambda values always. Okay, but this is actually for the m is equal to 9 case itself. For the m is equal to 9 case itself, suppose we are having a lambda value where we have a ln of lambda is equal to minus 18. Okay, and that will result in maybe this, but this almost very close fit. Okay, so that is one case. And this is actually maybe, okay, ln of okay, lambda is actually, say, suppose we are having ln of lambda is equal to 0. Okay, so whenever we choose such a say very large value, so in very large value, okay, you can see that this term is going to have a very large maybe influence on the total error. So that will result in maybe because this is, we know that if we fit a curve like this one, okay, that is going to have the maximum error. Okay, so that means whenever we have a ln of lambda, so that means lambda takes a very large value, okay, maybe very close to infinity, maybe theoretically, then this whole term will be very large. So that means the largest error. So this is a case of maybe a very large error. Okay, so likewise we can analyze the situation. Okay, and so that is maybe the significance of regularization. We will discuss this regularization maybe later when we discuss specific models, okay, in detail. But you should have the concept of what is regularization, and maybe the whenever we change the user controlled parameter lambda, okay, how that will have an impact on the total error, okay, and maybe how that will help us maybe in avoiding overfitting. Okay, so that is a important point here. And so suppose we plot the ERMS, okay, with respect to say the lambda is also taken into consideration. Okay, so then you can see that for very small values of lambda, okay, ln of lambda, okay, and maybe when it increases, okay, so how this training error and test error actually maybe say changing. Okay, so you can see that the test error is going to be very high. Okay, maybe for very large values. Okay, say so that you will have a, okay, ln of lambda is okay large in negative. Okay, and so that means the training error is actually okay very small. Okay, so likewise you can the same concept that we have discussed here is actually maybe shown in terms of a plot. Okay, so this is actually maybe the concept of regularization. And if you look into the polynomial, okay, you can see that maybe the same set of parameters that we plot, okay, for different values of, okay, log, okay, maybe lambda parameter. Okay, so maybe this is the best one, okay, that we have just see. Okay, again, so this will not be taken by the algorithm. Okay, or that will result in largest error. Okay, so that is a the analysis that we can actually obtain with respect to the parameter w and the different values of maybe regularization. Okay, so that is about maybe a simple example, or maybe a very general example, where we have seen how we can generate a set of points, okay, from a non-function sine 2px, and then we add some random noise, because we know that the usually the data that we obtain through different means will have either a noise or can be corrupted due to many interference. Okay, maybe if it is an instrument, there can be a lot of other interference. Okay, or there can be error while entering. Okay, there are a lot of chances of maybe some sort of error or say noise added to original say data. And we have seen the concept of maybe fitting a curve. Okay, and then we have seen the concept of overfitting, and then we have seen maybe the maybe a technique called a regularization that can be obtained to control, okay, the overfitting. Okay, and maybe deciding in the best model. Okay, so that is actually about this simple example. Or so this covers actually many important techniques or important issues, okay, that generally comes in a data, or sorry, pattern recognition or machine learning problem. And also then we have seen the importance of having large data size, that also we have seen. Okay, so there are a lot of interesting things. And we can one more point, here we have okay, in this particular polynomial, okay, that we have defined, one more thing is there. So that means here we have so there is a possibility of having multiple models. Okay, so that means here whenever we are having m takes different values, as we have seen for m is equal to 0, m is equal to 1, we have different models. So one is a maybe a parabolic, another one is a cubic. Okay, so or maybe maybe a sixth order polynomial. Each of these are different models. So that means there is a issue of selecting the best model also. Okay, that means which model M we have to find out. That is model selection is another maybe important issue that we have to solve or that we have to consider while designing pattern recognition problem. So there are many important issues, okay, or important maybe phases of maybe pattern recognition that we have seen in this example. So it's a very important thing that we have to always keep in mind. Okay, again, one more thing. Here we have seen one error function, okay, but you can define other error functions also, okay. So here we have selected maybe a square of the difference between the predicted value and the target value, but you can have a maybe say absolute value, okay, you don't need to take the square, or you can have another maybe cubic or maybe any other, okay, function that you can define. So that also we will see in later discussions. So there is another choice of maybe which error function is actually the best one, okay, and then the minimization of the error function. So all these are actually very important. So that means maybe so we can say that our problem is minimizing this function, as we have seen, and we define a polynomial function. So that is a polynomial function that we have seen, okay. And the model selection is actually choosing the parameter m in this case, okay. And then we have seen regularization, we are adding a penalty term, so that also we have seen, okay. And then so that is a maybe the maybe in a very brief manner what are the important things, okay. So far we have covered, and now we will go to entirely different thing, or we'll start with our original discussions on maybe probability theory, because that is very important actually in order to understand, okay, or in order to have uh, a base for maybe the topics that we will discuss in the coming classes, okay. So we will quickly go through some of the fundamentals of probability, okay. Maybe the definitions of various probability rules, okay, etc, etc, okay. So I think all of us know about the basics of probability. So assume that we are having we'll continue this discussion with an example, okay, which is taken from our textbook. Okay, assume that we have two boxes, okay. One box is red in color and another one is blue in color, okay. And so there are apples and oranges, okay, in the boxes. So we are having the first red box contains maybe six oranges and two apples, and the blue box actually contains okay three apples and one orange. Okay, so that is a scenario. Okay, so as we come across with any say a probability question, there can be a lot of questions you can actually ask to this particular situation. So maybe what is the probability that okay an apple is actually say selected at random okay from these two, okay. Or you can ask another question, so what is the probability that if orange is selected if the that say fruit is actually selected from the red box, okay. So there are a lot of things, and there can be say with replacement, without replacement. There are a lot of scenarios that you can maybe very complicated situations can be generated, and we can actually ask to okay find out the probability. So we will not be going into that type of discussion, okay, but we'll have a general discussion on maybe the concepts that are required to understand the pattern recognition, okay, using probability theory, okay. Especially a technical base in maybe say at a rule, okay, and its application in maybe pattern recognition. So that is our goal actually, okay. So this is assume that so we define maybe say two random variables, okay. So for example, suppose we are having a random variable called a box b, okay. So we define a random variable b. So I think you know about a variable, so that can take maybe say different values. Assume that here we define a random variable, so there are a lot of specific maybe I mean the things that is actually attached with the random variables and its analysis. So we are not going to that type of discussion here, but I assume that a box is actually okay, a random variable, okay, which can take maybe two values, either maybe red or say blue, okay, so which can take either red, okay, or it can take a value of b, okay, so that means either red or say blue, okay. So that is actually the two variables that can be taken by the random variable, okay, b, okay. And assume that for the time being, let us assume that the red, the probability or the 40 percentage of the time, so there's a chance that okay, the red box is selected, and 60 percentage we have the blue box is actually okay selected, okay. And we don't have any other say box also, so 40 percentage and 60 percentage, okay. So that is about the random variable b. Similarly, we can define another random variable, say f, okay, which corresponds to fruit, okay. So that can take again two values, either an apple A, okay, or it can take a value of O. So these are the two values that can be taken by the random variable F. So keep in mind that when you define a data set, okay, in a pattern recognition problem, we have seen that there's a feature vector, okay. So for example, in the case of sea bass and salmon discussion, we have seen that we can have a length, we can have a lightness, we can have a width of the fish, etc., etc. Okay, so each of them can be a random variable. Okay, so that means we can assume because they can take any value, okay, from maybe a set of values. So again, there can be different possibilities, whether some of the variables can take a discrete values, okay, or some of them can take a maybe continuous values. So that so all these discussions that we maybe go with this particular example is equally applicable with a feature vector of maybe any kind in our maybe pattern recognition say discussion. So that is a point, okay. So this is a typical scenario. We have two random variables b and f, okay, with the possible values they can actually take. And now assume that okay, we have a okay, and one more thing, assume that we have a okay, so in this case, suppose we generally define x and y as two random variables, okay. So that means we have a x can be b, okay, and y can be f, okay, or whatever way, okay. So but for in order to define the general rules of probability, supposedly we have a two variables x and y, okay. So x takes a set of values, okay. Assume that a discrete values here, and y also takes a set of discrete values. So that means x takes a values xi and y takes the values yj. So in this case, and assume that the different number of values, the total number of values that can be taken by x is m, okay. So that means there are m different values taken, and y is actually maybe l, okay. So that means l number of maybe different values are taken by y, okay. And so here this is a typical case, okay, of such scenario with the m is equal to 5, okay, because x actually takes 1 2 3 4 5 different values, and l takes 3 values, that is 1 2 and 3, okay. So for example, we assume that so for example, suppose x is a I mean suppose size of maybe a dress, okay, x is size of dress, okay. So that means say suppose we can have maybe say small, okay, maybe large, okay, then you can have a xl, okay, xxl, etc., etc. So assume that there are five, and maybe for smaller, okay, so there is a before a s itself you have one more value, okay. So they can say that that is one possibility. And why, let us say that the cost, okay, cost is actually whether low, okay, medium, or say large, something like that. So that is a way you can always associate typical scenarios with these random variables that we define. Okay, so we have a situation like this one. Okay, and if you look into each of the cell values, okay, they actually corresponds to whenever the random variable x takes a particular value. Okay, so for example, if you take this particular cell value, okay, this particular cell value, okay, so that means that count, okay, so that cell value will be representing as what is actually the total fraction of the total cases where we are considering, where x takes this particular value and y takes this particular value. Okay, so that is the way the meaning of each of the cell value. Okay, so assume that we are having say x takes xi, okay, x takes xi, okay, sorry, so x takes xi, okay, and y takes yj, okay, general cases. Okay, and we assume that the fraction of points, okay, among all the points, assume that there are in our data set, okay, suppose we x takes xi and y takes yj, there are nij points. So n is a total number of cases where x takes, that is a random variable x takes xi and y takes yj. So nij is the such total number of points. Okay, so based on that, we can maybe define, okay, different probabilities. And one more thing, assume that there are total, okay, ci, okay, points where, okay, we have a x takes maybe xi, that is a count of maybe, okay, total number of cases where x takes xi. Similarly, assume that we have the count of, okay, all the cases where we have y takes yj. So that means it is actually sum of this column and sum of this row. Each of them actually corresponds to maybe ci and rj. So these are the different maybe terms that can we can define with respect to this situation, considering two random variables and their discrete values they assume, okay, they can take it, and maybe the fraction of points, okay, among all the possible, how many points are actually taking these combinations of values by x and by y. Similarly, if when you consider a single maybe one column, okay, or maybe one feature alone in the feature vector, how many points are actually, okay, fraction of points are actually taking a particular value, okay, for that variable. So these are some of the terms that we must be clear, and based on that we will be maybe going to the definition of a set of probability rules. So I think that we will discuss in the next class. Okay, so thank I think we will stop for today, and we will continue from next class. Okay, so if you have any doubt or any clarification, we can discuss. Otherwise,